how's it going, AS Math? This is our last lesson of Intro to Mechanics. This is weight and normal force, and to kick us off, I have a question for you. What is the difference between mass and weight? Is there a difference? Can we use them interchangeably? I want you to talk to a partner next to you for like a minute, and then let's come back and share what you come up with, and go. All right, we're back. So really the key thing with mass and weight is, yes, they are different from each other. And if we think back to like F equals ma, the thing about weight is actually a force. And we know force is dependent upon the mass as well as the acceleration. So really, what is the difference here? Well, I went ahead and I sketched kind of just it's like a cute little drawing of somebody being on Earth and somebody being on Jupiter. And here's the thing. You probably have heard this before. Someone that's on Jupiter is going to weigh 17 times the amount they do that on Earth. So what I did was I made the weight a lot bigger, but notice the mass has not changed. Mass is really how much matter, how much stuff you're made out of, and that's not going to really change drastically based off your location. However, your weight can, depending on what planet you're on. And since weight is a force, and it's getting bigger on Jupiter, but the mass is staying the same, well, the only culprit is the acceleration must be changing. And in fact, that is what's going on. We're going to talk about that very quickly here. So mass is intrinsic, never changes on location, but weight is a force, and it is based on gravity. Okay. Well, if we know that F equals ma, well, the equation for weight is W equals mg. The weight of an object of mass m kilograms is given by W equals mg, and this is also known as the force due to gravity, where g is 10 meters per second squared. G is the universal gravitational constant on Earth. So it's never going to change for this course. We're going to round up from 9.8 to 10 and just use that guy as a gravitational acceleration. So that means if you're on Jupiter, this G will change when you're on Jupiter. It'll get a lot higher, but your mass isn't going to change. And this is really what weight is. Weight is just a force. And so let's use it to solve some problems. So, a ball of mass 0.2 kilograms is thrown vertically upward out of a window 4 meters above ground. The ball is released with speed 8 meters per second, assuming no air resistance. Find how long it takes to hit the ground. Okay, so we eventually want it to hit the ground. So what we're going to do is when we sketch this guy out, this is work example 2.3, page 43. When we sketch this guy out, we know the ball is going to be up in the air. So we know that that force of gravity is going to be acting down on it. We know it's W equals mg. Since it's going upward initially, we can assume that the acceleration in the direction of that motion is positive. And likewise, because this acceleration is upward, we can assume that gravitation due to Earth, that acceleration is going to be negative. So we're going to end up with some kind of negative weight force. We also know that U is equal to 8 meters per second, but the ball's released 4 meters above the ground. And so what we're going to do is we're actually going to assume that the displacement is going to be -4, because we're going to measure it from the top going down, and so we want that to be a negative displacement. Okay, so we're going to use this equation to find the time, because we have U, we have S, and we have A, actually, because it's -g. So we're going to plug those values in. So A is -g right there, the -10. And we end up getting some kind of quadratic out of this. Again, you guys can solve quadratics. You'll end up with 2 answers, but you can't have negative time. So we end up with 2 seconds for this ball to actually hit the ground. Okay, so not too bad. Really, the hard part is setting it up and kind of reasoning your way through it. Let's move on to part B and see what that guy has for us. So now it says, if instead there is a constant air resistance of 0.1 newtons against the direction of motion, find how long it takes for the ball to hit the ground. Okay, so kind of a similar situation, except this time we have air resistance that is going to be acting in the direction of motion. So this is from the instance it's going up. We have air resistance that's acting down. But when it's coming down too, we have air resistance that's also acting up. So we kind of have two situations that are going on the way up and on the way down. And if we want to find how long it takes for the ball to hit the ground, we're going to need to find the time it takes for it to get up and also for it to ultimately hit the ground and add those together. So on the way up, this is our first diagram that we have. Again, if this is on the way up, we're going to define up as positive because acceleration is going up. We also know the weight of the ball is going down. We also know the air resistance will be resisting that motion going up. And so F net equals ma. And so we can set this up where we have negative W minus 0.1 equals 0.2, which was the mass of this guy. And so we can find that A, as it's going up, is negative 10.5 meters per second squared, which is useful. So now we want to find that time. We also want to find that displacement. So let's find the max height time. Well, we could use V equals U plus AT. We still have U is equal to that 8 meters per second. That did not change. But what about V, right? Well, let's think about it. If it's an object going up and it's going to start coming back down, at some point at the apex of its height, its velocity should be 0 because it is not speeding up. There is no speed. It's just dead up here. So V is actually going to equal 0 for that, and we can use that to find T. And really, this is time 1. So we plug our values in. We end up getting that for T1. Now we want to find that height that is reached because, well, if we are considering two different times, right, we need to find the total displacement in order for us to make sure that time makes sense, or else we're just going to be getting, right now we just have the time it takes for it to get up here. If we do it from the top and it comes down, we'll only get that time from the top to the bottom. We want that whole time. So we do need to find the heights. Well, we know it's thrown from 4 meters up, so that's one of our heights, but this is kind of the other one that we're going to need to add on to that, okay? So we can plug in our values again, and then we can find that S is going to be 3.05 meters, okay, going up. Now going down is going to be that 4 meters that we got earlier that was given to us in the problem. So we have now, we have our S1, our T1. Now we can draw the diagram going the way down. So not a lot of change. The only thing is now our acceleration is going down because the ball is going in that motion. And we also know the air resistance force is now opposing the motion again, going the other way. So once again, we know F equals ma. So we can take both of those forces. We know that it's going to be a positive 2 this time because it's helping the acceleration. That's the direction we're going now. And so when we subtract those, the mass didn't change. We find the overall acceleration is going to be 9.5 meters per second squared. And so now we can find that second displacement. Actually, we don't really need to do a calculation to find the second displacement because we know it was that 4 meters given to us in the beginning, the first part of the problem, and then plus that additional meters that we found earlier with that first part, with the first diagram. So we can actually set this up and put it in for here, and then we can actually just solve for the second time it takes for the ball to hit the ground. Once we have that time, we can add it to the other time, and voila, we got everything we need. So let's set this up. We have 3.05 plus 4 equals 4.75 t subscript 2 to the second power. And once again, you're going to end up with two values. You're going to throw out the one that's negative, okay? So you get the positive. Now we can add that to our first time, and so we end up getting 1.98 seconds total. That was a lot. That was a lot, all right? So let's move on now to our last part of this, which is the normal contact force. And really, this is kind of like Newton's third law a little bit. I don't want to say it's completely like it because Most of the time, people are referring to the contact force as just like between like like a Sharpie and like the ground, or like my hand right here. And that's not completely Newton's third law. It's not a complete reactionary force, but we can kind of assume it is, at least for these problems. So if I have some kind of object sitting on a table and it has a weight, well, why isn't it going through the table? Why isn't it falling through it? That's because the table is actually exerting a force up as well. We call that force R. At least that's how we denote it. R just denotes the normal contact force. Now, instead of saying normal contact force every single time, if you just say the normal, I will know exactly what you're talking about. And if I say the normal, now hopefully you know what I'm talking about. Just a reaction force, like a surface on an object. And it's usually the same magnitude as weight to prevent an object going through the surface. And that kind of makes sense. If I have an object resting in my hand, it is in equilibrium. There is no net force on it. So they usually cancel out. Okay? Although there are instances in real life where if you have a really, really heavy object and you set it like on an unstable surface, it might break through because there's not enough force to hold it up, so it just goes through. The one thing to note, though, is that it is always perpendicular to the surface, no matter what. Again, Sharpie in my hand, the force acting up is perpendicular to my hand. And so that actually has a unique twist to it if we do tilt our surfaces. We're not going to yet, but eventually we will. And so our weight is still going to be acting down. It acts towards the center of the Earth. But the contact force is going to be perpendicular to that surface. Again, you won't need to consider this yet, but it's an interesting idea to run with for future problems. So let's see an example. This is worked example 2.5 in your book. So it is on page 43. Okay. So a crane is lifting a pallet that rests a stone of mass 5 kilograms. The motion is vertically upwards. The crane lifts a pallet from rest to a speed of 3 meters per second, 6 meters. Find the normal contact force on the stone block during acceleration. So we have a stone resting on a pallet. The stone has a weight to it, but the pallet has its own reactionary force going up. So for our diagram, this is kind of what we have to work with. Here's the pallet surface. Here's our stone that looks beautifully cut, a beautiful ingot. And so we really want to figure out what this R is. And let's use the information we were given. So we know that F net is equal to MA. So we know that it's going to be R minus W equals MA. We know the weight is 5G, or it's going to be 50 newtons. V equals 3 meters per second. U is equal to 0 because it starts at rest, and S is at 6 meters. So if we set this guy up, we can use this Suvat equation to find A. We find what A is, and then we plug it back in for here. And so we know what W, M, and A are. So it's all about just kind of rearranging this guy and then finding what R is. Okay? And that's our lesson for today. If you need more help, look at those worked examples. I didn't go through every single part of the problems on purpose, so you can look at them yourselves. And if you need more help, once again, we can talk about this stuff on a later date.